We have seen now with binary search, we are focusing still on binary search trees, and we have seen operations that we can implement on top of binary search trees. For example, traversing the tree in order, post order, pre order, and so on. We saw also how to search for an element in a binary search tree. If you notice, none of these operations changes the tree, right? Because we are not removing anything from it, we are not adding anything to it, we are not updating any keys in it. So these operations do not change anything about the tree. So if the structure of the tree was good to begin with, it's good as well at the end. If the structure of the tree was bad to begin with, again, it's a chain that has very, very big height. The same thing is going to happen after we implement the operation. But as I said, sets in computer science are usually dynamic. We add to them, we remove to them. If the binary search tree that I'm maintaining corresponds to or stores the set of grades of the students in my course or the student IDs in my course, well, students enroll in the course, drop the course even during the semester. So the set can expand, the set can shrink, depending on whether students are joining the class or dropping the class. These operations are going to change the properties of the tree, or the height of the tree, for example, and so on. And we have to be careful, because binary search trees have that property that all the keys in the left subtree of X must be smaller than the key of X, smaller than or equal to the key of X. And all the keys in the right subtree of X must be greater than or equal to the key of X. So if this is X here, and we have, this is the left and this is the right, the Y dot key must be smaller than or equal to X dot key for every Y in the left subtree, and Z dot key must be greater than or equal to X dot key for every Z in the right subtree here. Okay, so two operations that we need to worry about are what happens when we insert an element into the binary search tree, what happens when we delete an element from the binary search tree. What do I mean by worry about? Is that we need to maintain the property that this is a binary search tree, which is again the property about the keys. So I will start with inserting into a binary search tree. So if we have thinking about, for example, BST insert, and here we have, let's say, T and element Z. So imagine that I have a tree T, and when I talk about T is that I usually have access, basically it's pointing to the root of the tree, okay? And I want to insert an object Z, it's a node Z, but has some key here, okay? So this is Z dot key, and we need to enter it. It's now at this point, it doesn't have any left child, right child, or anything like that. We just need to enter something with the specific key, okay? And insertion is actually easy in a binary search tree. We will always insert the new key as a leaf node, okay? So let's actually illustrate it. I'm not gonna write the pseudocode again, because you should be able to write it on your own, and you should be able to implement it on your own. But let us illustrate with a simple binary search tree here. So let's imagine that we have this binary search tree. We have key 20 here, we have key 10, and we have key 15 and 18. And then I have here, let's say 5 and 2, 9. Let's say here I have 30, sorry, it cannot be 31, it can be 25, and this can be 31. And suppose I want to insert the value, let's say the value 17, okay? So suppose I want to insert 17 now. So I want to do BST insert on this tree and the key 17, okay? So I want to now, after I'm done, I want the tree to have an additional node that has the key 17 in it. Well, okay, how do we do that? So I come first to the root. I have access to that. When I talk about T, I can look at T dot t dot root, for example, t dot root is the root of the tree. Okay, so when we talk about t dot root, so this is a property of the tree t, and the root basically give me access to that. So this is now I'm pointing to the root. I look at the key in the root, it's 20. I'm trying to insert 17. 17 is smaller than 20. Then I say the 17 has to go into the left subtree of 20. It has to go somewhere here, right? So it has to go to the left of 20 because 17 is smaller than or equal to 20. Then I come to 10 here. Now I check the 10. Is 17 smaller than or equal to it? No. So the 17 must go to the right of 10. So I now go here. I look at 15. Is 17 smaller than 15? No. It is greater than 15. It has to go to the right of 15. Then I got to 18. And is it smaller or larger than 18? It is smaller. Therefore, it has to go to the left of 18. Now, 18 has no left child. Therefore, now I am done. I basically create a left child of 18 and I give it the key 17. And this is what insertion does, really. That's all it does, because you just look at the root and compare. If it's the key you are inserting is smaller, go left. If the key you are inserting is greater, go right. You keep doing this, going left and right based on that simple test until you get to a node that if you want to go left, if it doesn't have a left child, you now add your new key as a left child. And if you need to go right and the key, the node that you are inserting to doesn't have a right child, you now just add it to the right of that one. Okay? So if I wanted to add 19, for example, I would have done exactly the same thing. I would have gone to the left of 20, 19. I now go to the right of 10, and 19 is greater than 15. I go to the right of 15. I look at 18. It has to go to the right, and it is added here. Okay? Very, very simple algorithm. Now, what is the running time of this algorithm? Once again, look what happened here. Since 17 was smaller than 20, I completely ignored the right subtree of 20. When I got to 10, 17 is greater than 10, I completely ignored the left subtree of 10. So in general, the number of operations can be much smaller than n, depending on the structure of the tree. The factor or the parameter that is controlling everything in the worst case is once again the height of the tree. Because in the worst case, the key that needs to be inserted has to be, we have to traverse the longest path from the root to a leaf to be able to insert that. So in the worst case, running time is O of h, where h is the height of the tree. Okay? So if you think about it again, in the worst case, you have to traverse the longest path from the root to a leaf, and then insert that new key as a child, left or right child of that leaf. That's gonna take on the order of the height of the tree.